the chapter on wave optics is an immediate progression from the chapter on superposition, because we're going to start off with a simple case. I have a screen. Well, I have two planes. So let's say they're both screens, but one has, in the most elementary sense, and yes, two holes are more elementary in this case than one hole is, two slits in them. Now, approaching let's say that we have a light source. And the light source is very, very far away. So far away that basically these waves of light that are coming at the screen, we can think of them as planes parallel to each other. For example, if you look at the Earth, you look at a globe, the Earth is round. But you look at a lot of places. You can find a lot of places in like central Wisconsin where if you go to a part of the Earth and you look around and so like, the marshland, it's like, no, it looks flat from where I am right here. Or if you go out onto one of the lakes, it does not look spherical, it looks flat. Because we are a great enough distance away from the point. If we want to draw sunlight coming to the Earth and we don't, care about like, which is, like Nebraska farther away from the sun than Wisconsin? No. We could treat the light coming from the sun as plane waves at this distance. So it's far enough away that we don't have to worry about like, the distance from each point. It's just a plane wave. So that each one of these is getting the same light. Light at the same wavelength, the same speed, therefore the same frequency. And because it's the same light hitting both of these at the same time, if there's a phase difference, when we pick t equals 0 to start, it's still the same. Which means that if I want to look at any given point, then the result at this point let's just say right now the amplitude depends on the phase difference between those two light rays. For example, if this one were able to go, if the light was able to go 100,027,032.3 wavelengths from the screen, from the hole to the screen, and this wave we're able to go 100,027,016.3, let's say 0.32 wavelengths from this hole to the screen. The only thing that would be important is the fact that that 0.32 was the same in both cases. Then we'd see, okay, both cases, they're in phase. Both cases, they're evened out. Now, let's see, if I take a look at this, then so forgetting about that integer, which is important, all that we care about is any possible difference between how those move. If I were to take some case, so this distance d2, say that was equal to the distance d1 plus exactly one wavelength. Well, what would happen here is that right here, those two waves would agree in phase, and so the two maxima would be together, they'd both be in phase, and so they constructively interfere. You would get a maximum right here. Now, at this center point, because it's the center point, you see a maximum right here. And in this case, the maximum is going to translate to a bright spot. So you're going to see a bright spot at the center because those two paths are exactly the same length. And at any point where those two paths are exactly an integer number of wavelengths apart, the waves will be in phase and you'll get a bright spot. So I get a bright spot here and a bright spot here. Well, if I'm getting two bright spots there, that kind of implies I'm getting a dark spot somewhere in the middle. Where? Well, in this case, that would be where d2 is equal to d1 plus half a wavelength. Then these two waves, from each of these, I'm treating each of these holes as the source of a light wave. And because the light coming through those holes, the light that I'm treating as two different sources, is from the same light wave, we know they've got the same wavelength, the same speed, the same frequency, then at that point where the distance is, where the distance taken by, along path d2, where that's equal to d1 plus 1/2 a wavelength, at that point, that gives me destructive interference. Or a dark spot. Now, technically, I need to describe these in terms of those angles. And as long as this separation L is way larger than the slit separation D. D? Seriously, sadly, yes, D. As long as L is much larger than D, then those two angles are pretty much exactly the same. Now, I can look at those in terms of angles, but for double slit interference, I could say, all right, the angles are at it depends on the path length. There has to be some number, some integral number, 0, 1, 2, 3, 4, whatever, of wavelengths divided by the distance between the slits. But since that angle, theta, is close to, if I call that y, and that L, then I can look at this and say, okay, whoops, the tangent of theta is equal to y over L, which is equal to, well, you know, if theta is small, and how small? Theta less than about 10 degrees or so. The tangent of theta is pretty much equal to the sine of theta is pretty much equal to theta itself in radians. So, for the double slit, I could write theta is pretty much equal to y over L is equal to m times lambda over d, or I can find the location of the bright spots by going through and taking these integers, 1, 0, 1, 2, 3, 4, etc., times a distance, lambda, times, units of length, times L, the separation between the screens, units of length, divided by, so I've got units of length squared, divided by the distance between the slits, units of length, so I'm back to units of length, and I've times an integer, so for, as long as the angle's small, less than 10 degrees, I can use this formula to find the location of all the bright spots. And in the same way, I can find the location of the dark spots halfway between the bright spots. So I just put this, write this as m plus 1/2. And there we go.